Hi, this video is all about simple linear regression model, a really good start-off point in talking about the ordinary least squares estimator, which is a standard workhorse in econometric analysis. Now, you have probably seen this in your slide packets already, but the motivation of using OLS is to provide an empirical grounding to the concepts or the theories that we have already established in the area of economics, right? So economists love stories, right? We love making stories. We love making conjectures regarding human phenomena. So let's have a simple story, right? Suppose you were asked to provide or to examine the relationship between a person's wage and a person's work experience. Now, let's suppose that at a conceptual level, you already have an idea of what that relationship looks like. So let me type it here. Let's say that you wanted to look at log of wage as a response variable or a dependent variable. And at the conceptual level, you already know that it is a function of, say, work experience. Now, this line one, or this first equation, this general equation that we're showing here, is what we call your economic theory, or this encapsulates the economic theory or the economic model, in a sense that it shows you that there is a relationship between log of wage and there's a relationship between wage and experience. Now the thing is, we cannot just focus. You cannot just focus on concept alone, right? You cannot just focus on theory alone. You should also have some grounding to reality, right? Now, that grounding to reality comes when we start constructing and we construct our empirical model. So to make this realistic, of course, it may make sense at a conceptual level, but we have to make this realistic by constructing our empirical model, right? Or our econometric model. Now, our econometric model must capture something measurable, right? Something that you can measure in reality, right? So let's just say that you have a data. Of course, the assumption here is that you have your data for wage. You can observe a person's wage, all right? You can capture a person's wage, and let's be more explicit here. This is log of wage. And let's say that we have some parameters, beta naught plus beta 1 times experience plus some random error epsilon. Now, this is going to be your econometric model. Now, what makes this realistic is that wage and experience are now measurable, right? And we are fitting this relationship, we're fitting this linear relationship between wages and the person's work experience with an additional error term captured by E. All right. Now, you already know this in your slides that E is a random error. It's an error term. It's a random variable with mean assumed to have a mean of 0 and variance sigma squared. Of course, those are unobserved. Those are unobserved parameters. Right? Your sigma is or sigma squared. Your variance is an unobserved parameter. Right. So we now have our econometric model. Right? We now have our empirical model, which we can now measure. Right? Now, establishing this relationship between wage and experience would be possible, or we can ascertain that there's a relationship, and we can measure the direction or the magnitude of such relationship when we identify or when we get the values for beta naught and beta 1. Now, at this level, beta naught and beta 1 are still unobserved. Right? We still don't know. We still don't know the exact value. We don't know the exact value of beta naught and beta 1. We just know that there are these parameters. We just know that these parameters exist, and these parameters capture the relationship between wage and experience. Now, how will we get beta naught and beta 1? Right? We can only make a guess. Right? We can only make a systematic guess, and this systematic guess is what we're going to do via estimation. Right? So we're going to estimate beta naught and beta 1 using the data that we have on wage and experience. And this is where your knowledge of statistics come in. comes in, right? So you have you have an unknown parameter, right? You know that this parameter exists, right? But you don't know the exact value of the parameter, right? And we are going to guess the value of that parameter using estimation. Now, in econometrics, we have our basic, we have our usual estimator called the ordinary least squares estimation. And later on, we will see why we call this ordinary least squares estimation. All right. So let's try to run, let's try to estimate this equation, this empirical model using OLS. All right. So this is named OLS. So let me set up the directory first. So we have seen this in the previous videos now. So let me just type cd just to change the directory. All right. So we have here, you have these folders. Right. Let's peg it at this folder, because this contains the wage data. Let's paste this. Right. And let's say that we have an existing data on wage named wage1. So you have use wage1.dta. Right. Just make sure that there's no other data set loaded. We type in clear. Okay, so let's save this first. So the dataset is now loaded. You can see it in your screen. It's already loaded. You can see it in the variables window. We already have wage1. Now, we run OLS. We can run OLS by typing regress lwage. There's already a variable for log of wage here, and experience. We're not gonna type, of course, if some of you might ask, why don't we include the error term? Well, the error term is not observed. It's at the population level. It's something that you cannot measure, right? It captures everything. It captures the characteristics of your dependent variable that cannot be captured, that cannot be measured, all right? So it's practically well, the distribution of this error term is practically zero, right? And they cannot be measured, so we don't really include them as a regressor. We don't include that as part of our syntax, right? So let's run this, right? And we get these results, right? Now, the reason why it's called OLS estimator is basically we are linearizing, we're sort of linearizing the relationship between log of wage and experience, right? We're trying to fit a line. We're trying to fit a line that encapsulates the relationship between wage and experience. And maybe one strategy, one thing that can convince you that we're trying to fit a line here is if I try to plot this log of wage with experience. Right? So let's try to run two-way scatter experience. And let's add another fitted line, LOH experience, just to ensure that we are looking at two graphs. Right? Okay. So see, we're trying to fit. So this is your data points. This is your data points that capture that compare your years of potential experience with log of wage, right? With log of wage. Now, this red line is practically the red line is practically your OLS results, or it captures your OLS results, right? So it shows you the best line. It shows you the best line that captures or that fits this data, that fits this set of points well, right? Now, by best fit, we mean that the distance, the squared distance between the actual points of y and this line is at the minimum. Hence the term ordinary least squares, right? we are minimizing, we're practically coming up with a line. We want to find a line with these characteristics, with these parameters, such that the squared distance, or the square errors, as we call it, right? The square distance between the actual data point and that line must be at the minimum, right? Must be at the lowest, right? In other words, this line must capture, must fit this data pretty well, right? It must fit the data, it must fit this data really well. And this line will sort of characterize the relationship between log of wage and experience. All right. So that's why you call it OLS. Right? Now, one may ask, why don't we just use correlation if we're just trying to compare two variables? Now, here's an advantage of OLS over a simple correlation. Simple correlation just tells you that there is a co-movement, there is a strong co-movement, or probably a strong diversion between two variables, but it doesn't necessarily tell you the magnitude at which your dependent variable changes with respect to a regressor, an independent variable. That's something captured by OLS. So the coefficient column here, right, something that we haven't done in the previous video, unfortunately, but at least at this stage, we can now see what really happens. So the coefficient here captures how log of wage changes for each unit of experience, or for each additional year of experience. How does log of wage, how does an average person's wage change for each additional each additional year of experience? Now, this is already in your slides, but since log of wage is in log terms, right, we're looking at partial elasticity. By partial elasticity, we mean that this parameter, or sorry, this estimate, this parameter estimate 0.004 is actually, when we interpret this actually means that for each additional year of experience, we are seeing, we would see on average an increase of 0.44% in level wages, in the person's wages. So it's actually really small. It's actually really small, and probably it's sort of evident in your graph, right? In your scatter plots. So pretty evident, right? So log of wage, or wage, doesn't really respond that much, but it's still, as later on we'll discuss more of, is still significant, right? But the effect, or the magnitude, is pretty small. So that's what beta 1 is. This number here is an estimate, is a guess. It's a guess for beta 1, right? It's an estimate for beta 1, right? And the estimate for beta naught is 1.55. Now, what does this intercept, or what does this constant mean? This constant is practically the value, the average wage, average log of wage, or in general terms, the average of your dependent variable when all of the regressors are equal to 0. So assuming 0 years of experience, the average log of wage for a given person is around 1.55, right? So that's how you interpret the constant. Now, in some applications, the constant may not be relevant, but it's worth looking at, especially if the intercept is weird, or if the values of the intercept is weird. Now, how would we know if the parameters, how would you know if the estimates are weird? Well, of course, we will have a sense of the correctness of the estimate if we visit the literature, and if we have established very well the link between your conceptual framework, or your economic model, with your empirical model. The soundness of your economic model matters in interpreting the results of your empirical model. Assuming that your empirical model is correct, right? The best way to interpret these particular results, is if you have a sound economic model. If economic model makes sense, and if it is grounded on valid literature, if it's grounded on a lot of studies, if it's grounded on stylized facts, right? So that's how you establish the correctness. That gives you a sense of whether the estimates are correct or not, right? So in a more practical level, this is your regression results. Now, let me just describe a couple of things here, a couple of things that you're seeing here. We have your number of observations, right? So it tells you how many observations in the sample were included in this estimation. Now, the thing here is that OLS will always get the lowest available number of observations. So if you have some issue of missing data, so for instance, you have 526 observations, but for your dependent variable, but your independent variable only has say 300, then OLS will just use 300 observations, right? All of those rows with missing observations will be automatically dropped from the analysis. And that's a reminder, so you don't really need to drop observations ex ante, right? OLS, the regress command, will do this for you, right? You also have your R squared, which is a measurement of a goodness of fit, right? So it's just one of the measures of the goodness of fit. And in the next video, maybe I will emphasize it a bit, right? That R squared is not really something that you should be looking at. That shouldn't be your primary metric of interest if you're looking at the goodness of it, or if you're trying to verify whether the model is correct or not. Okay. What else? We have your adjusted R squared, right? That accounts for the statistical significance of your regressors, right? And you have your root mean squared error. Okay. And you also have your ANOVA components here, although ANOVA doesn't really make sense here because you have two continuous variables being analyzed. Okay. So this just decomposes the variance, the variability of your dependent variable relative to the independent variable and the unobserved terms, which is the residual. So this is your unobserved variability in your unobserved. Okay. Now, let's talk about the second column, right? Standard error. Right? The standard error relates to the variance. It relates to the variance of your error term. Well, of course, this standard error is the standard error of the OLS estimator, right? Recall that OLS is an estimator, right? It's OLS estimator is a random, and as an estimator, it is a random variable, right? This estimator can assume different values depending on the sample. So if we do this experiment over and over again, we will most certainly get different coefficient values for experience, right? So we can plot that distribution. So when we have different samples, so when we observe different samples and plot the estimates obtained from those samples, we will have a distribution. And of course, if it is a distribution, and since OLS is a random variable, it will have a measure of spread. And that measure of spread is captured by your standard error, right? So the lower the standard error is, the more efficient OLS is, right? In a sense that the variability, the spread of the estimates around the true population value, around the parameter value beta 1 is smaller, right? It will be smaller. Right? Maybe in the next video we will I'll show you a couple of simulations to examine or to demonstrate how this variability, how the standard error of OLS works, right? So, but at this point, the standard error measures the spread of the OLS estimator. Right? How efficient OLS is in estimating this parameter beta 1. Is it too spread, right? Or it's not? Now, the spread, or that spread of OLS estimator, that variability has an impact on testing the statistical significance of the parameter estimate. All right. So aside from measuring the magnitude of your parameter, right? We also wanted to test, right? We also wanted to test whether it is statistically significant or not, right? And when we know when a variable is statistically significant, it means that at the population level, when you do this experiment over and over again, holding a fixed level of significance, say 5%, 1%, 10%, you know this in your stats already, right? It just means that at the population level, we know that the coefficient of experience is not zero, and there is indeed a relationship between the two. In other words, a test of significance just tells us whether this relationship is true or not at a population level, right? This also validates our conceptual framework whether the relationship is true or not. Okay. So that's the purpose of your standard errors, right? The lower the standard error is, the higher the likelihood that you're gonna have a statistically significant um, regressor, right? Statistically significant regressor for this model. Okay. Now, these results look nice, right? So it just tells you, well, the magnitude is a little small, but it's sort of intuitive, right? More work experience, since given the sign of the coefficient. Of course, the sign also matters. Other than the magnitude, the sign also matters. Given the positive sign of the coefficient, right, it tells you that wage responds positively with respect to experience. It decreases by about 0.4%. A little small, but fine. It's still positive, 0.4% for each additional year of experience. Now, here's the thing. These results are valid. These results are valid only if the Gauss Markov assumptions are true, or if the Gauss Markov assumptions hold, right? What are those assumptions? You have those 5 assumptions, right? You have your linearity in parameters. Let's try to check if that's true. As a linear regression model, line 3 satisfies the first assumption. You have linear parameters, of course. You have linear parameters. We have established this ex ante that your empirical model is linear. Hence, assumption 1 is true. A second assumption is random sampling. Right? This is a Wooldridge data set, so maybe we can just assume that the observations are randomly sampled. But in real life, randomly sampled, random sampling is sort of difficult, if not costly, especially if you wanted to capture a sample that is representative of the population that you're looking at. If you're just going to do convenience sampling, or if you're using a data that is drawn from a convenience sampling exercise, then random sampling may not hold true. And this will have an effect on your coefficients, right? This will have an effect on your coefficient estimates, right? And the results might be misleading, or in econometric terms, might be biased, right? Right. Now, biasness, you already had this, just a quick recap. Biasness means that if you do the sampling over and over again and run the estimates over and over again, the expected value of those estimates, the average of all those estimates, will not hit the true population value, or will not hit the true parameter value beta 1. Okay. Number 3, you have your no perfect collinearity, but it doesn't really apply here because you just have one regressor. Number 4, and most important of those 5, is your zero conditional mean assumption. Zero conditional mean assumption states that your experience, your regressor must not be correlated with the error term, right? Or in more technical sense, the expected value of E conditional on experience must be equal to 0. A lighter assumption for consistency, but this applies to large samples, is if the covariance of E is that the covariance of the error term and experience must be 0. Why does it matter, right? Zero conditional mean assumption matters because we want to have a precise measurement of the effect of experience on log of wage. If this assumption is violated, then the effect of experience, or beta 1, will capture not only the effect of experience, but also the correlation of experience with all the other unobserved factors that are embedded in the error term E. Now take note that the error term captures everything else, captures all of those unobserved factors that could affect wage. Right? captures everything else that can affect wage other than experience. So if experience is in any way related to any of those unobserved factors, then beta 1 will capture not only experience, not only the effect of experience, it will also capture the effect of all the other unobserved factors. Hence the term confounding, right? It's as if your experience, the parameter beta 1 is sort of confounded, right? Or your experience is confounded in the sense that there are other factors that could be affecting experience, right? And this will have an impact on beta 1. So the measurement of beta 1 will now be incorrect. Right? When we try to estimate this model, right, with all of those confounding factors embedded in the error term, the measurement, the estimate of beta 1 will be biased, or OLS will be biased. Okay? It will give us estimates that are far off from the true population value, beta 1. The fifth assumption is homoskedasticity, right? Just means that the variance of the error term must be constant. Variance of the error term conditional on the regressor must be constant. Right? In other words, as experience changes or as experience increases, the variability of the error term must not change. If that happens, the standard errors, if there is heteroskedasticity, the standard errors will be invalid. Right? That invalidates the standard errors because it means that your standard errors will be varying, right? Your standard errors will be varying depending on the size of your regressor or your independent variable, right? And that will have an effect on testing your significance, testing the significance of the independent variable. It affects the validity. In other words, it affects the validity of the test. It affects the validity of your test, and of course, the results will not be really useful. And this will not tell you anything useful if if OLS is biased, right? If one of those assumptions are violated. Right. Right. And that's the reason why we don't normally use simple linear regression models in actual analysis. If we just wanted to compare as it is without establishing any inference or without establishing any conclusions about the relationship between Y and X, LWH and experience, then simple linear regression will work. But in most practical applications, we normally construct a more comprehensive model that includes all the other possible factors that can affect experience, right? That can affect X, right? But of course, this is still informed. This is still informed by theory. Right? It doesn't necessarily mean that you'll just have to include everything in your regression model the way you wanted it. It should still be informed by theory. It should still be informed by your conceptual framework. You're not just gonna dump in any variables that you like in order to make an effect appear, right? It should still be informed by theory. Right? So that concludes our video using Stata. In the second part of the video, I'm going to show you how to run this, how R produces the same output from the scatter plots to the regressions, right? How R produces OLS, simple linear regression, in the same way that Stata produces it. And in the next video, we're going to show an example of multiple linear regression model and how specifically we're going to show how the partialing out effect works, right? Why do we need to partial out, right? What's the advantage of using a multiple linear regression model compared to a simple linear regression model? Right, so this is the second part of the video just to show you how to run the same procedure using R. Right, now the concepts are already in the first part of the video, but if you wanted to replicate it using R, that's also fine. Now, it's a little programming heavy when we do this in R, but of course the premise still holds. So let me just, maybe you can do it from here, right? We already have an existing sorry about that. We already have an existing code for the same data set. So let me just run this. Right? Make sure that the libraries are loaded. You have your tidyverse, Arsenal, Haven, Outreg. This is for tabular summary stats. Right? Right, now that the data set is loaded, let's try to run the regression. So let's assign an object name for the regression. Let's say it's M1. Right, now to run the regression, we have LM, right, LM function, and we will specify the formula. So the formula is simple. You just have L wage on experience, right? And it's called the data. The data is the data frame. Okay. After generating this object, we can take a look at a detailed presentation of that model results by typing summary M1. Right. So this shows you the regression estimates. Right? So this is the coefficient for experience. This is identical. This is identical to our regression results earlier. Right? And the nice thing here is that it's already indexed with significance codes, right? In Stata, you just have to look. You have to look at the p-values. Right? You have to look at the p-values. If the p-value is closer to 0, then it is statistically significant. Or specifically, if your p-value is lower than your level of significance cutoff, say 0.5, 0.05, if it's below 5%, then it's statistically significant at 5%. In this case, the p-value is at 0.11 or 0.01 or 0.011, which means that it's statistically significant at, it's basically statistically significant at 1%, or rather at 5%. Right? It's statistically significant at 5%. It's above 1%. It's above 1%, but it's below 5%. So it's still statistically significant. Right? And you also have your estimate. You also have your estimate for the intercept, which just tells you the value or the average value of log of wage when experience is 0. Of course, not setting an independent variable 0 may not make sense all the time. So it depends on the model that you're trying to construct. Now, if you wanted to replicate the scatter plot that we did earlier, I admit that R produces a better plot than Stata, right? The plot, the graphing utility of Stata is a little old. Right? It's a little old. I mean, it's old looking, right? So let's try to create a plot here. So you have ggplot, all the data set. We have a scatter plot, so it should be geom point. Right? Let's identify the dependent variables. Let's identify the variables. You have experience, you have y, L wage. So that will generate the scatter plot. Right? You can also set the color, or you can set the size later on, but that doesn't really matter. So, yeah. And you have your fitted line. So you can create the fitted line by typing geom smooth, right? So we have our method, which is lm, and then we'll specify the variables. You have x experience, you have y lh. Enter, and that is your regression line, which is pretty much the same. It's pretty much the same as our earlier plotting using Stata. So that concludes our video on simple linear regression model. And hopefully in the next video we're going to do the multiple linear regression model, specifically on the partialing out effect and the trade-off of omitting variables and including irrelevant variables in your model.